N95 mask, I think we will have flattened the curve. We can't do that. So what we are trying to do is find materials that can give you more protection than some of the materials that many people are using. I mean, if cloth masks had been effective, that would be fine, and they are effective to some extent. But again, I think the point is to try and find uh, materials that can be yet better than the common materials like cloth. So that's really what started one part of this work. The second part is, in places like India and Africa and many other places, an N95 mask is not affordable. Today, I think an N95 mask, if you can get it for about $5, you're doing well. In non-constrained times, an N95 mask in bulk can be bought for about 20 cents. But that's not today. And that kind of a price at $5 or even $3 is just not affordable by even medical personnel in India or third world countries. So they're using materials that really are not effective at all. So our goal was to try and find something that is cheap, readily available. And of course, there's another aspect to this, that even if we had N95 masks, the distribution channels are not so great. So getting these masks delivered to people all over the world is not so simple. So we were looking for something that is locally available, readily available, and can be fabricated into a mask at a fairly low cost, either through local craftsmen or some low-cost, low capital-intensive industry. And so that's where we've been concentrating on. So yeah, based on a conversation with some faculty members, and there was a suggestion that smoke detectors can detect very small particles, and it seemed that if they can do that, then can we convert a smoke detector into something that can detect virus-sized particles? And so that Irene and I started looking at that, and we first made a very simple device where it was a container with a hand pump, and we wanted to draw air through the membrane, through whatever material it was, and see if particles of 0.3 microns or less were being blocked. Now, so how do we generate particles of 0.3 microns or less? It turns out that incense smoke can do that. And Irene can tell you about how we've verified that is indeed the case. So this diagram sort of roughly explains how this process works. We've got a smoke generator, which is just an incense stick, and then we have a hand pump, which you see on the other end of the diagram, and we draw the air into a chamber, which is pretty much airtight, except the only way of air coming in is through the membrane or through the face mask filter. And then there's a one-way valve that makes sure that the air doesn't go back. Now, this pump is fairly cheap. Again, a couple of bucks. So this whole apparatus is probably under $10. We are using a smoke detector that is radiation-based. We haven't tried one that is based on light. If someone wants to try it, just go ahead and do that. But at some point, what we found was we tried this and we checked different materials. So of course, the standard was how long does it take for cloth? Well, one extreme was how long does it take for cloth to be penetrated by the smoke particles, and it turns out it's only about 3 or 4 puffs. So each time you press this air pump, it's a puff. And then we tried some more complicated materials like N95, and it took forever. It took about 500 puffs for N95 to be penetrated. Initially, it was less, but we've been tightening the equipment a bit. So initially, it was somewhere in the order of 300 350 puffs before the smoke alarm would go off. So I don't know about everyone else, but I'm very sensitive to smoke alarm noise. So we just modified the smoke alarm so that it wouldn't generate such a high pitch. And then later we've done some more modifications because it's a very tedious process. So we wanted something, counting the puffs is also not straightforward, but we'll talk about that later.
At the beginning, when I first started thinking about this problem, I was very tied up on how to generate the aerosol of particles that was nano-sized, and that drove me like down a rabbit hole. And then Mandir already was doing this with the incense, and I was like, this is genius. So turns out that the incense particles are naturally with a size distribution which is between about 100 nanometers to a half a micron in diameter. And that's obviously very easy to generate, and it couples very well with using the smoke detector as a particle detector, because obviously incense smoke is smoke. So here is some results from published data, where on the left we have the size distribution, so that's the number of particles that have each of these diameters that they measure. On the left is for incense, on the right is for a variety of just normal things that people do. So if you look at the graph on the left, you can see how the diameter of these incense smoke particles are between 0.1 microns and about 1 or 2 microns. And on the right, we see the same type of information. So the diameter of the particles that we expel when we do, for example, speaking, sustained vocalization. I think they describe it as just saying ah for 5 seconds or something like that. And then voluntary coughing. And you can see that in all cases, the size of the particles that we expel when we do those actions is actually around 0.7 microns or so. So very similar, in the same range than the incense particles. So we thought that the incense particle, well, Mandir thought that the incense particles would be a very good replacement for simulation of person-produced droplets that could contain the virus. So that's why when we say that a material is good to stop a specific particle size, in our case, we chose the particle size so that it's very similar to what humans do. But of course, we can't have people coughing on cloth masks all the time. So this was a very, very clever way of going around this issue.
So as I said, we started making this, and I've got to say this, there were a couple of students involved. One student, Jake Doherty, specifically, who helped and actually came up with some very good ideas during the process. So I asked him to modify the smoke detector, and he found a container, an airtight container. We tried a number of different airtight containers, and so this is the version 1 of the, actually this is probably version 2 of the smoke detector based tester. Put a cone so that we could take samples and wrap them on a plastic cup, and then insert them in a similar cup that was attached to the container, the airtight container. The red container is the airtight container, and there's what you're seeing there is some material that's being tested, and this glass jar is our smoke chamber. You see a rod in the glass jar, that's the incense stick, and we light the incense stick and it fills up with smoke. And I think it is a very, very harsh test, in the sense that it's unlikely that you will have that density of virus particles, but it is a way of checking. So then when we press the pump, you can just see the blue line in the back next to the red container, and we'll see the details later. So that's where we exhaust the air from, and so the air comes from the glass jar through the red container, and it's drawn by the pump. And so when the smoke is detected in the red container, you'll notice there's a breadboard in front, and there's a LED, and that goes off, and you can reset it with this red button here. So that was the basic model. Now, it worked fine. It did discriminate between good materials and not so good materials. Um, there were several problems with this, but we kept using it. We tested maybe hundreds of materials with this.
One of the first things we did was actually checking that the incense particles that we were generating with the incense stick, that was actually the size that we wanted. So we use an instrument that's called a scanning electron microscope that has very high resolution, and it allows us to see these particles in 100 nanometers range, or even if they were smaller, we could see them. And what we did was putting these small substrates, so small, just flat, clean surfaces that would capture some of these incense particles, and then analyze those in our electron microscope. And we confirmed that the size of the incense smoke particles was in the range that we were expecting them to be. So they're between 2 microns, the largest ones, and the smaller ones, we found particles that are 50 nanometers or around that range. So we consider that to be a good replacement or a good substitute for naturally exhaled particles.
Yeah, so this is a much later version, modification of the test chamber. So as I said, it's pretty tedious to run this manually. So we rigged up some test apparatus that can compress that air pump. It's like a ventilator, but of course it doesn't do everything the ventilator does, but it does press the pump, and we were able to make this in our workshop. And you'll notice there's a quick return mechanism. So there are some details of how you need to make this. Paul Furs from Tiverton also helped a lot. So what we want is we want the downstroke to be at a reasonable speed, but this pump is spring loaded. So every upward stroke is about is driven by the same spring. So the second thing is the air volume that's taken expelled is in the range of what a human lung would either breathe in or breathe out. And so now what we did was, and Jake did this, he rigged this pump up to the smoke detector, and what this does is when the alarm goes off, so there's an LED on the LCD on this test rig now, and it counts the number of puffs. So when the smoke detector detects smoke, in addition to lighting the LED, it also stops the motor. It's a DC motor in this case, and tells us how many puffs are recorded before the material was penetrated. So that's and of course the other thing you'll notice in this is we've changed the container. We tried a lot of containers. This particular container is very nice because it's got a gasket on it, and if you put some kind of Vaseline on right around the gasket. We bought this at a local not consignment, it's like a big lot store called Job Lot. And we found that we were able to create a fairly airtight container. And then, of course, the coupling was the last thing that became a very useful way of sealing and changing samples. So that coupling you're seeing on the container is just a PVC coupling. Home Depot has a bunch of them. We bought the 1-inch coupling, and we connected it. We've used, I've become a big fan of hot glue, and we used hot glue to connect it. And of course, we checked to see that there was no leakage. We used the typical the soap bubbles and soap solution. And instead of sucking out of the container, you pass air into the container, and if there's any leakages, the soapy liquid will show bubbles. So we went in and checked and made sure there were no leakages. So if there was a leakage, we added more hot glue and sealed it. And then this is ready for as a test apparatus. So this device is a little more complicated to make, but it's not super difficult, and we will be sharing more details on how to make it in a video as well. So the halyard, for example, has become my test now.
Okay.
It is. So if the halyard typically, if it goes beyond, it's somewhere in 5 to 10 now.
Okay.
Where the variability comes in is how dense the smoke is in the smoke chamber.
Yeah.
But we are trying to reduce that too by by sort of calibrating it so that we will keep the smoke density in the smoke chamber to within a certain number.
Okay.
By injecting fresh air to make sure that it doesn't get overloaded. Sometimes we can see the difference that sometimes it's really chock full of particles, sometimes it's not so full. So I think that's what causes the difference. But there is never enough variation that it's always within a fairly narrow range. So one material will always be, I sort of categorize them as class A, B, C, D. A is, of course, the best materials, which is your N95s, which go currently in the test apparatus we have, they have 300-400 puffs or higher. B is from 50 to about 300 puffs. C is from about 10 to 15 puffs to 50 puffs. And D is anything less than that. So again, it's a rough classification, but I'm finding that works for my tests. So cloth, for example, is D. If you use any combinations of many different kinds of things, we found majority of the materials are D. Some of the new materials we are trying with the cellulose-based materials, many of them end up in C. So they may be 2-3 times more effective than cloth, but there's no guarantee that it's going to be 5 times more effective. But in general, the C materials 10 to 50 is typically what we are calling C. We do come across materials that end up in the B category, where they are somewhere in the range of 50 to 300. So, for example, Filtrete from 3M, that material ends up in sort of the B category. It's somewhere between 70 to 90 puffs. And then, of course, the N95s and some materials we've made that just end up 300 puffs plus. Those I call the A materials.
Using the same technique that we used to measure the particle size of the incense, we looked at the particles that go through an N95 filter material using the same technique, and you put these substrates, these clean flat surfaces inside of the smoke chamber now, so on the smoke detector chamber, so on the other side of the N95, and then we capture these electron microscopy images, and we saw that the particle size that we see after the particles have gone through the N95 filter, after the material has failed, is similar to the size distribution that we were finding for the source incense, but mostly small particles. So we found a lot of particles that are 500 nanometers or less. So basically what that means, as we expected, is that the N95 filter filters a lot of the big stuff, and eventually it lets through some of the small stuff, which is what we expect to do for most filter materials.
Okay, so this is a table. What we are doing is, with the particle counter, we've also started writing to disk, writing the data as well. This is something that we just ran earlier today, where you can see that at 1 o'clock we ran this. So this is a count of the particles, and I'll make a graph out of it. So this is before I lit the incense. So this is 0.3 microns or less, 0.5 microns or less, 1 micron, etc. So this is cumulative in a sense.
Yeah.
Not in a sense, it is. And then you'll notice that what happens is, so if I take this data at column B and I plot it,
So that's over time.
yeah, there you go.
Oh, nice.
All right, so
we've got a few minutes before the next session starts, and did want to mention that Mandir and Irene will be returning in the video that starts at about half an hour on alternative filter materials. But we did have one question I have a couple of questions from the audience. One is the expectation that carbon or soot is harder to filter than liquid-borne virus?
I'll answer that. Yes, it is. Well, so liquid-borne particles would be larger. And can you hear me?
I can hear you. Yes, you're coming through great.
Yeah. So we haven't checked the substrate deposition of aerosols or liquid-borne particles, but they generally are bigger. So carbon and viruses would be carried in these liquid particles, and so we expect that they are bigger. Yeah, so that's the answer. Irene, if you have something to add.
Just for similar size particles, like assuming a droplet of liquid or a particle of carbon or soot of the same size, it's going to depend on the surface charge a little bit as well. So it's difficult to say in general, but we consider that it's going to be similar if they are the same size.
Great. All right. And we had one other question, which was, did you see any variation between incense brands / types? And what brand type did you use for most testing? And also, do you have any links to papers? Or I think we could just paste in the link to Rapid Solvers, right? I'll paste that into the chat because that's where you'll be publishing things, right?
Yes. So incense types, we didn't see a difference. We bought the cheapest incense from the dollar store. And it's a good question. But again, we weren't really investigating that because once we found that we were looking at particles that are 50 nanometers or so, we didn't search anymore. As far as papers are concerned, we expect to put a lot of material up through rapid solvers, but I think we should put a more sort of concentrated manuscript up as well. We'll get to that once we are done with making masks. So, but you can always email us for information. We'd be happy to help.
All right. Excellent. Well, thank you very much. You will be back in about half an hour. So I'm going to start with our next presentation, emergency ventilators from ambubags, and I'll see if we can bring on the presenters from that once that video is done. So I'm going to just get that set up, and we'll get it going.
In this business for about 45 years. I got my PhD from the State University of New York, Stony Brook in 1976. I came up here as an assistant professor. I got a chance to take a leave of absence, work with a small company called Datascope in New Jersey. They got to be a pretty good sized company where I learned the intra-aortic balloon business. I did my PhD in the simulation of cardiac assist mechanics and things of that nature. And we've been working on a variety of things where you apply engineering skills to medicine, and it's been a fun ride. The most recent company was called Life Recovery Systems, and we started that a few years ago to get cooling devices for people who need to have their body temperature reduced following a cardiac arrest. That's still around now, but this opportunity came along. We thought that we could take some of the devices that I've built into aortic balloon pumps. That's a cardiac assist device. And I had a number of those older devices in my lab and in my garage here, and said, well, we could probably take some of those devices and convert them into ventilators, because the basic parts of them are pretty much the same thing.
So I am a product designer. I got involved with this through Rhode Island Orthopedic, who I've worked with on various projects, and we have been, and so it was an introduction from Doug Moore, and he introduced me to Gregory J. and to Bill. I had already been sort of feeling the same way and struggling with, been developing some mechanical type ventilators, more what they would call bag squeezers, and, you know, went through a few different versions of that. And then, of course, I was introduced to Dr. Ole here, and we've been back and forth since working. Myself, I'm at doing product design. I graduated Rhode Island School of Design with a BFA, BID. I've had a company here for over 35, 40 years now, Fulcrum Product Development, where we developed all different types of products. I've worked extensively in the medical field, where we've developed IV transport systems and, you know, all of the air systems behind the hospital beds. So a lot of in-house architecture for hospitals, as well as many different types of consumer products. So for me, this is sort of a natural extension to what I do, and I'm hoping to package this with this team and see if we can make this work.
Okay, well, I know I've known Dr. J from Greg J, and I go back about 20 years when we tried to do we're doing another startup on resuscitation, a cooling device. And Greg was pretty impressive, because he volunteered to get into the suit system that we built in the lab. So we've gone on and off over the last 20 years collaborating on a variety of things. And when the ventilator stuff came up, he's the one I talked to right away, and knowing that he had control of the simulation lab up at Rhode Island Hospital, where we've got there's a number of different patient simulators that are great for experimenting with and learning about resuscitation. Kunal and I talked initially when I came back. I was from France right before everything broke here. We were under Department of Health quarantine, so I talked with Kunal over the internet and by telephone, and said we really need to do something, because the things that I saw happening in Italy at the time when I was in Europe, and starting to happen in France, that was not going to be good here. We needed to really do something, and he agreed, and so that's how we got started on this, all of these projects that we've eventually called, I think, the URI Rapid Solvers. And Kunal was instrumental in setting that up, and with a lot of the communication over the web and things like that with his network. And he was able to move around a little bit because he wasn't under quarantine. And that's how we got things started. We know that several weeks ago, we thought that ventilators were going to be in real short supply in Rhode Island. And in fact, I made a phone call to South County Hospital here to see if, that's our local community hospital, to see if they had ventilators and were able to do pulmonary support. They said, yes, they had some, but they weren't sure they were going to have enough. And I knew that Greg J was up in Rhode Island Hospital, and as in the emergency medicine department on the front lines, and he said the same thing. We think that there might be a real problem in Rhode Island because the caseload was going up pretty quickly. But the governor sort of stepped in, and as you know, we've had the lockdown here, and that's been reasonably effective. Right. So it looks like we're going to be okay for the time being.
As long as it stays flat.
As long as it stays flat.
I started thinking, looking at ventilators, thinking that there could be something that could be made that is more of a from common materials, and that's the same approach that Bill has been taking. So I'm, and I think that there'll be other parts of the world where if we can create a roadmap for people, they can find different components that will be able to work in those ways. And that's what my hope is to develop this so it is, that there might be swappable parts that would be good enough to work.
Well, the parts that are in the system are ones that I pulled out of an intra-aortic balloon pump. The materials are pretty straightforward, pretty simple. And ventilators generally don't have to run as long as the 25 million cycle point, but it depends on how long people are on them and so on. The device needs to be controlled, and the Arduino is a pretty it's a little device that we use in our sophomore laboratory experience here for electrical and computer engineers. It's a nice little device. It's reasonably reliable and very inexpensive and used all over the place in a variety of systems and designs. So and it's so straightforward. We thought that would be the way to get it out and use that device as opposed to some other complicated microcontroller. Because they are so prevalent and pretty straightforward to use. What we're doing here overall is we know that there's a device called an EMBU bag and that's one of the commercial devices. It's basically a bag with some valves on it that gets squeezed over top of a person's mouth and nose to squeeze air into their lungs and then allow that air to escape afterwards. And it's squeezed by hand. And it's often used as for temporary support because it is rather straightforward and very simple. So the idea is that if we could automate one of those and not have to squeeze it by hand every time, that would be a pretty effective ventilator that's relatively simple. So we started with that as a concept, and we know that we can move devices called air cylinders with negative and positive pressure on the cylinder, and that'll cause an excursion of about the same amount as you can get with the fingers and your thumb of your hand. It's about 5 to 6 inches. So we started with a pneumatic cylinder with a excursion of about 5 inches. And I said, well, how do we get one of those to move? Well, if we have a source of pressure and vacuum from a pumping system, that's pretty generic, and we run that through a regulator that controls the pressure so it doesn't overpressurize things. And then we have a couple of things called solenoid valves that open and close under computer control. So the computer sends a signal, opens the valve, and air goes through. Sends another control signal back, and it closes the solenoid valve. We have 2 valves in the system because we were interested in using both pressure and vacuum. We wanted to be able to send the pneumatic cylinder off in one direction and then bring it back in the other direction using vacuum. And so we've got a pressure solenoid valve and a vacuum solenoid valve. They're basically the same device. The vacuum solenoid valve is always open unless it's been activated. So that means the cylinder stays back in a resting state away from the bag. And then the pressure solenoid valve, that's normally closed, and it only is open when the microcontroller sends a signal to it. So the way the system works is we have several different controls going into the microcontroller, one for the inspire time. How long does it take to inspire, to get the breath in? And then how long do you want to hold that breath? And then how long do you want the exhalation time to be? And all three of those together control what the overall breathing rate is. So each one of those is based on time, and the controls going in are right now we've got it set up with simply with potentiometers that are variable resistors, but they could also be controlled by just with an Arduino by just putting in a number using the computer keyboard. But this will work with just the microcontroller itself and 3 potentiometers. And so you set those time limits up, and nominally for the inspire time, I think we're using a couple of hundred, about 200 milliseconds, a hold time of about 100 milliseconds, and then exhalation time so that the entire breath cycle comes out being about an overall cycle rate of about 10 to 12 times a minute, and then that can be adjusted depending upon what the clinician wants to have happen. It's got a vacuum input and a pressure input, and then an out to the ambu bag, and the rest is just plumbing, as they say. I've got a pressure gauge and a vacuum gauge. You really don't need those. There's a pressure regulator that's reasonably important to keep pressures down, depending upon what comes out of your of the compressor. And there's a vacuum solenoid and a pressure solenoid, and the other thing you see here, there's a copper colored device in the center. That's just a little accumulator to store energy during the cycle, but not really needed. And the rest is just interconnecting plumbing. But the plumbing here is all copper because of when it was built originally. So you can replace all of that with just plastic hoses, and cable ties are actually pretty effective in sealing them. So if we could easily make this whole thing out of plastic plumbing parts. Well, you can see the chest rise and fall on that's the patient simulator controller. That's the patient, simulated patient, and you can see the chest rise with the breath. And then that's the box that we put everything in at the end, and with the compressor sitting alongside. And the compressor we're using here is a fairly beefy one, but it's one that's used in septic systems, and this is an aerator for a septic system design. This is I think about 10 cubic feet per minute at about maybe 4.5 cubic feet per minute at about 10 psi.
I started coming up with different concepts. I have several other mechanical ones prior to this, but when I started to work with Bill, I was looking at different ways of doing the pneumatic cylinders. And we originally talked about, you could actually make this with a 50 cc syringe, or you could take a piece of pipe and make a piston from that, or a bought air piston. And so I was looking at different ways of configuring this. And the one you see here is a simplified version. It is not an ambubag version. The other one, if you flip to it, you'll see that I was not that one, the other one. Yeah, this one in the background there, that's made all from just standard plumbing parts. So I started to take just standard like PVC, T-shaped plumbing parts and start to put them together. And then of course I went to the plumbing store and I bought all kinds of big pieces of plumbing parts, and I said, this is way too big. You know, it was just way too bulky and way too big. It doesn't matter. I can show you. It just seemed out of place for the ambubag. So then I started to look at maybe making it more simplified. And, do we need an ambubag? I know that there's a lot of different ventilator versions that use the ambu-bag, but what if we just incorporated a piston into this instead of, and made that the whole mechanism instead of that? And that would be up to our team on, we wanted to keep with that, the ambu-bag concept. So that's based on everything that, that's been working so far. The one on the left, basically a syringe, or, and then the one on the right would be more of an air cylinder, just a standard air cylinder that could be bolted on based on one of the ones that Bill was speccing. And the way that I was putting this together, I started to put this together as just simple sheets of plywood, laser cut or table saw cut, that could get slid together. And then the other components that we're talking about, all of those other plumbing part, pneumatic components, could get bolted into this framework. So that's the direction that I started to work from. But so you can see on the right, it's basically just some sheets of material that would just, you know, slid together. And then I made it an option to slide it either way, slide it horizontally or slide it vertically. So this is the same, this is actually the same piece. The one on the left is assembled together with basically an air, a standard little piston air cylinder or a syringe. And then the one on the right is the thing exploded to just to show how simple it could be. And then from this, we could put all types of different pathways and holes into it for all of the different, you know, PVC, plumbing, whatever, and connect it and bolt it all into just different panels at the same time. So that's where I'm at with it. What it's going to take is, it's going to take me starting to draw out all of the different components, or figure out what the different sizes are on that, and so somebody could take and use whatever they have available that is close to what will work, and bolt it into a framework like this. It's based off of what was done on the video, what Bill had done on the video here. So I was just trying to simplify the way you, although I do like, you know, pieces of wood and drywall screws and all that. I was trying to clean that up just a little bit.
Yeah, no, it's fine.
You know, if somebody doesn't have an ambu bag, can we take the same plumbing, the same mechanism, and use it with a simple cylinder? That was my approach to it on that earlier version. So, which is a question. I don't, if it can be, but if the ambu bag is sufficient, then.
Well, if you do that, you have to add the valves, and you have to have some way to limit the excursion in some reasonable way. Otherwise, you can do potential damage.
Yep.
So that was the reason I shied away from that for the time being. But we could develop a system that directly, you know, there's a couple different ways you could do that. You could do a bladder sort of thing that went back and forth based on pressure, on the pressure applied, and sort of a conical shape, for example, and that would work fine. So it's a number of different things that we could do.
Because your approach, I guess, is it's using minimum pressure to. I noticed that some other ventilators out there, they need a lot more power than what you need with the way your approach, because you're able to operate this thing on just a very low pressure, just a syringe.
Right. So, yeah, this is there's about 6 psi going into the syringe.
Right.
So,
it's amazing. Yeah.
And it's 50 cc. So, you know, you do that 12 times a minute, and that's how much airflow you need.
Mm-hmm.
I'm gonna unmute here. Well, we've got a few more minutes. I see that Bill is here. You're muted though, Bill. So let's see.
There you go. Can you
There
hear
we
me
go.
okay?
Yes, yeah. So I don't see any questions, but I was wondering if you had any thoughts on where this project was going to go next.
Well, we'll update our website, so there'll be pretty precise instructions on how to put one of these together if somebody needs to. And we'll probably be developing an academic paper on some of this as well, and take it from there. Our business is educating people, so that's what we try to do.
Great. And so what are the, what are the improvements or tweaks you're looking at? Are you going to continue to use ambu bags, or you're looking at using other types of bladder type devices for
Well,
that?
we'll take a close look at that and see if we could put something together that avoids the use of an ambu bag and is even simpler. But we haven't done that just yet.
All right, great. Well, we're going to take a little, just like a 5-minute break, unless you had anything else. Oh, we did just have a question. We have 2 questions now. One, how do you clean the inner air pathways after constructing the device?
The ambu bag is a one-time use device, and that is the air passage. And that's why we use that design. So the compressor and all of those passages, those all stay separate as long as the ambu bag is intact. And that's a basic principle that we use in the intra-aortic balloon pump system as well.
Great. And one other question was, would an electric linear piston make it more portable?
We haven't looked at the energetics of that, but because originally we thought that most tertiary care centers have air supply as well, and we thought that that would be a way to run this as well. But yes, you could use an electrical drive. There are some devices that do that, but to us it was more complicated mechanically to do that. And then you worry about device failure and things of that nature, where these compressors that we're using are really good for a very long time. The ones that are used to aerate septic systems go in the ground for 15 to 20 years.
All right. Great. And one last question was one-time use, but how long? I think that the question is about the ambu bag.
We haven't tested that, so that's really a good question. It's the membrane of the ambu bag is a fairly beefy silicon, and based on that, it's those are very similar to the bladders that I've built for intra-aortic balloon pump systems, and those went 25 million cycles. So I think that 25 million is probably reasonable for an ambu bag, even though typically the way they're used now manually, they don't get near that length of time.
All right. Well, thank you very much. We'll be back in about 4 minutes with a presentation from Mandir Sodhi and Irene Andrew on alternative filter materials. And just, yep, that was it for the questions on this one. So thanks a lot. Appreciate it.
Fully covered whenever they go into the hot zone. A lot of places that are having a very difficult time getting supplies right now. Tremendous help.
First layer is a critical layer, and we have to make sure that this is running smoothly, and then we only have to monitor it. But you have to be here a long time to make sure that the printers are running, because otherwise we have a lot of waste of production time and waste of filament, which is quite expensive. Try to stay here until 7 p.m. in the evening, have my dinner, and then come back at 9 to stay here until 11. to watch for the printers and restart them again at 11 so that they run 24/7. Try to be here 12 or 13 hours a day. We will produce about 200 a day now. We produce about 1,500 so far. We are getting more and more demand for it. I had an administrator who came to pick up 600 face shields for nursing homes, and she was so thankful, and I think she said thank you 15 times in 10 seconds, so that was amazing. She's so thankful because we produce something that can protect their staff.
Fully covered whenever they go into the hot zone. A lot of places that are having a very difficult time getting supplies right now. Tremendous help.
First layer is a critical layer, and we have to make sure that this is running smoothly, and then we only have to monitor it. But you have to be here a long time to make sure that the printers are running, because otherwise we have a lot of waste of production time and waste of filament, which is quite expensive. Try to stay here until 7 p.m. in the evening, have my dinner, and then come back at 9 to stay here until 11 to watch for the printers and restart them again at 11 so that they run 24/7. Try to be here 12 or 13 hours a day. We will produce about
All right. Well, we're going to start another presentation here. Thanks everybody for joining us. We're broadcasting from Rhode Island, showcasing a number of projects that have been featured and that have come out of collaborations in Rhode Island. And the next one up is a follow-up to one we showed earlier on testing filter materials. This one looks at some alternative filter materials, and we're going to get that started right now.
I'm Mandir. I'm a professor of industrial engineering at the University of Rhode Island. I got my bachelor's from India, Jadavpur University, and then I did my MS and PhD at the University of Arizona in Tucson. I've been here at URI for a long time, but I spent time in other places. I worked for about a year with NATO in Italy, and then I spent a year in Braunschweig, Germany. I do a fair amount of work with companies on manufacturing consulting. So my research interests are manufacturing engineering, systems engineering, manufacturing processes, sustainable manufacturing, logistics, and scheduling. So yeah, these are some of my core interests.
So I'm Irene. I am the director of the Rhode Island Consortium for Nanoscience and Nanotechnology at the University of Rhode Island. So I manage a lot of different microscopes. Mostly the electron microscopes are the ones that we use for this work. My background is in physics, and I got all my schooling, my bachelor's, master's in physics, and PhD at the University of Zaragoza in Spain. And I've worked on a variety of material science projects with a focus on nanotechnology. Oh, of course, sorry, that's the pump. Okay, so my research interests have been in a variety of material science related topics, mostly focused on nanotechnology for biomedical applications, although I've worked also on energy, water electrolyzers, safety of nanomaterials.
So our goal was to try and find something that gives that is cheap, readily available. And of course, there's another aspect to this, that even if we had N95 masks, the distribution channels are not so great. So getting these masks delivered to people all over the world is not so simple. So we were looking for something that is locally available, readily available, and can be fabricated into a mask at a fairly low cost, either through local craftsmen or some low-cost, low capital-intensive industry. And so that's where we've been concentrating. So if I want to make really thin masks, if they can give me the protection, I can do it with a vacuum forming method. The press can give me thicker masks, and we are still not sure which one will be the best approach. If the thin masks can give me the protection, they give me the breathability, that I've checked. But the protection is the issue now. They certainly give me the protection of cloth. That's not an issue. But cloth is no big deal. I mean, anyone can get cloth. If they give me twice the protection of cloth, I'm happy. If they can go higher than twice the protection of cloth with some reasonable thickness and breathability, I think we've got some blends that we are trying that actually do. These are blends mostly of cellulose of different kinds, like either paper and cotton.
Do you think it's more important how you make these paper-based masks, or what paper you use? Like, what do you think is the material, like your source material, or is it whether you use like a vacuum mold, or how much you blend them? I don't know.
So I'll tell you that tomorrow.
Okay.
I'll tell you why. Because we've so far, the material we have plenty of is the brown paper material.
Yeah.
We also have a lot of the newsprint material, which I will use today. So today I plan to make masks of two more materials, newsprint and cotton linters. And they'll all be about the same thickness. And then I will measure which one makes the better mask. Physically, they should be similar. But the question is, protection-wise, which gives me the better one? That I'm doing today. The paper itself is breathable if it is recomposed. So the paper, we've tried many different types of paper. So as I said, the brown paper seems to work very well, brown paper that people use in bags. And then there's the newsprint, which we are going to try today. Newsprint now does not involve petroleum-based ink. So if it is soy-based ink, it shouldn't be a problem. If it is petroleum-based ink, it has to be de-inked. But there's so much of this material around that it's, it's like it'll cost next to nothing to use that. The paper has to be, to use it, you have to shred the paper. So either in one of these home shredders, it's better if you have a crush shredder, so you make as small shred as possible. And once you're done with that, then you need to put it in a blender and blend it to the smoothie setting. And that seems to be pretty decent. Once you do that, then you can take the water out. So you'll find that there's a lot of water. You can use a sponge to take off a lot of water, and then you can hand dry it. The problem, of course, with hand construction is how do you make a uniform thickness? On the vacuum suction side, you want to the amount of water should be high, so you can then suck it. If you're doing a mold-based preparation, you do want a certain amount of water so that the material can flow into the mold. And when the mold presses down, it spreads the material. It doesn't get stuck to the mold. So again, all three methods can work. The mold itself can be made. We've made molds with plaster of Paris. They work fairly well. You can use a 3D mask to start the mold. We are going to be making silicone molds. That's a bit more expensive. A plaster of Paris is a very cheap mold material and available throughout the world. So either that, and vacuum suction isn't that difficult. It does need a vacuum source, So we've been using a shop vac, a small shop vac to do it, and so that simple shop vac will do the job.
All right. Well, that's that for this session, and we do have a little bit of remaining time here. So Irene, Mandir, and anybody else really from the panel, what we have up next at noon is a panel on the community feedback loop, sort of the process and things that we learned as a group supporting the community. But Irene and Manbir, did you have anything you wanted to add?
I see a question about coffee filters.
Yes,
which
there
I don't
was.
think we answered before. So Manbir did test coffee filters, and if I recall correctly, they didn't perform very well. So they perform similarly to cloth masks. And I want to emphasize one thing. We are comparing the materials that we're testing against N95 performance, which is obviously the golden standard, right? So if a material performs similar to cloth mask, obviously that's not the same level of protection that an N95 mask would provide you, but it would still protect you some. And the other thing to consider is that we're measuring against the incense particles, the incense smoke particles, which are relatively in the small range. But the particles that you expel when you speak, like the ones that are immediately close to your mouth, those are larger than the ones that we're actually measuring using the incense smoke. So even if the performance compared to an N95 is not good, it still does something. Now, whether a coffee filter does anything better than just regular cotton face masks, like the ones that all the makers and seamstresses are doing right now, I wouldn't say so, but maybe Manbir has a different insight.
No, I think Irene said it well. We've checked coffee filters. We've put 2 layers of coffee filters. We put 4 layers of coffee filters, and they fail very, very quickly. I've also tested filter material that's used for filtering in chemical labs.
All right, great.
Some of those are more difficult to breathe through. You can get those filters in various configurations, 3 microns. I think you can even get 1 micron filters. I think the one we were testing was 3 micron, and that paper, again, our check was that it didn't do that well.
Yep.
So I wouldn't recommend it.
And discussing materials, you also tested different fabrics, right? And they were all pretty similar.
Yeah, I think we checked canvas. See, the issue is there are 2 dimensions, the breathability and the protection. So some materials, most woven materials do not work well. When there's a regular weave pattern, it does not work well. When there is some randomness, which is non-wovens, depending on how that's done. So the electrospun materials are non-wovens in a sense. They don't have a specific pattern, and they seem to be fairly good at catching small particles. So the same is with the cellulose materials. When you reconstitute them, they construct a random pattern, and that's what we. If the openings in those random patterns are small enough that air can get through, so air, oxygen, and hydrogen, those are in angstroms. The size of those molecules is maybe 3 angstroms, 5 angstroms, which is 0.003 nanometers. Those are, I think it is 0.03. If Irene is the physics person, she'd know the relationship between angstroms and nanometers. Angstrom is 10 to the power minus 10, correct?
It's 1/10 of a nanometer, yeah.
Yeah, 1/10. So those are, that's right. So that's 0.3 nanometers. We are looking at 50 nanometers. So So air can get through. Virus, the N95 virus, sorry, the coronavirus is about 50 to 125. I'm not sure. There may be a precise number, but I don't know. I've seen numbers from 50 to 125 nanometers for the coronavirus size. But regardless, it is much bigger than air particles. So the point is, can we trap those particles and let air through? And so that's really the thinking behind all this.
Great. We had another question, and well, a couple of questions. What about shop towels?
No, it doesn't work. Tried it.
Tried shop towels? They didn't work.
I tried all types of them. Tried Scott towels. Tried paper towels. Tried tissue papers. Nothing. They don't work well.
All right. And another question, and I think the answer to this is to go to the Rapid Solvers website, is are the results by materials available? And they will be, right?
Yeah, this is my bad. I've been promising these results. We have some gross sort of categorizations. I think Irene has done a great job in trying to put some filter materials up on the Rapid Solver site. So there's this filter material from Rigid, which is the V6000 filter material. Now these are HEPA filters. We've tried HEPA filters. The concern with HEPA filters was that they may shed particles during breathing. They perform very well. Irene, you had something to say on the HEPA filters about how they should be handled. So I'll let you talk about it.
Yeah, the main issue. So we tried a series of household materials, and from the things that we could get our hands on easily, the best performing thing was HEPA filters, similar to the ones that you have in AC systems. The problem with those is that when they are solid, like when you have the whole thing, they're actually pretty safe, like they don't shed anything. But the moment you cut them, bend them, rip them, accidentally or on purpose, they start releasing glass fibers, and those are pretty nasty. They can give you thermal reactions, and also they're very, very bad if you breathe them. Like it's similar to asbestos, basically. So the HEPA filters could be a potential household material that you could use to improve your face mask, but you have to be extremely careful when you're making the mask itself. So when you cut the material, you have to seal the edges so that it doesn't release anything. So in general, unless you're being super careful, I wouldn't recommend going through a HEPA filter, like AC filter system. In terms of household materials that we tested, paper towels, coffee filters, these shop towels, all these things, as far as I remember, they all perform relatively poorly. But again, remember that these are against these like aerosolized, very small particles. They still give you protection when you're wearing them. Because your particles are very big, you are still stopping those. So it's one layer of protection. But yeah, and also I wanted to say that I didn't put the information on the website. It was Dylan who did it, was doing all the website thingy. Yeah.
Thank you.
All right, we've got another question. And all tests are just material and not implemented in a face mask, correct? And that you might want to speak to that, because I understand that at the moment you are now punching out pieces of material and running them through the filter apparatus, but you have ongoing work to build and fit and design face masks as well with this material, right?
Yeah, so the face mask, we're making something that will let us test leakage. So that's what we've got, is a mannequin head. And again, I'm a bit behind in getting this ready, but we've got a mannequin head. We've made an airtight box, and we are going to be injecting smoke into that box. We've built airways through that mannequin head that will mimic our respiratory airways. And then we'll take the mask and put it on this mannequin to see how much smoke gets through. As opposed to, so really it's quite a similar, in principle it's similar to what we have, except instead of a membrane, now we are going to put a head into a box and check that. Where we hopefully today. That's yeah.
if I can add one little remark on the filter test, on the fit testing. So we are, as you said, for now, we're only testing the filter material itself. And one of the reasons why Mandir was talking so much about breathability is because the harder your breathability is, it stops being less important how well your filter filters, because if it's hard to breathe, the air pressure inside of the mask is going to make the air go through, like by the noses or in the holes. So a material that has a high breathability and a low filtering capacity might actually, when it's actually physically in a mask, it might actually be better than a material with a very high filtration efficiency but a very hard breathability, because when you have a material that's very hard to breathe in, it's just not filtering anything because all the air is going around the edges. So that's something that, as Mandir said, we should be testing. We haven't been able to do yet, but it's a very important thing. And that's something that you can actually test when you're making your mask or whatever. Like if you feel the air is going through your, like you can feel it in your eyelashes, it's probably not sealing very well.
So there's one more test that you can do. Actually, this you could do at home, is to use some kind of a dye. And there are a couple of things. You can either use dye or you can use flour. Flour is very fine particles. I'm not suggesting you spray yourself with flour, but we'll be doing it with a mannequin. If you put a mask on and there's an environment with some flour, when you take the mask off, if you see any flower patterns on your face or the mannequin, that means there's leakage.
You could do it with curcumin, with turmeric or curry,
Oh,
because it's
good. Oh,
fluorescent.
that's a good thing.
It's fluorescent with a with a
Oh, I
UV
didn't
light.
know that. Okay,
Yeah.
good. Thank you for that. Yeah. All right.
And we had one last question, which was, is there a way that you can share a homemade step-by-step process
For what?
for doing everything that they're everything, building the masks or the apparatus, for example?
We have some, and again, I keep promising this. It's just that this takes away from the work, the time that we are actually testing it. But I think your question is valid in that unless we do it, it's not useful. So I'm going to make a commitment that by next Wednesday we'll have something on rapid solvers.
All right. I'll make a commitment that I'll help you with that.
All right. Thank you so much, Brian. Brian, I have to thank Brian for everything he's done. Yeah.
The handheld one, like the one where you're just doing it by hand, though, I think that's pretty self-explanatory if they go onto your YouTube channel,
Yes, you're
because
right.
you have good views there. Obviously, the Arduino stuff is not there, but like the manual one is pretty self-explanatory. I'm not an engineer, and I understand what's going on there. So,
great.
Yeah.
And this sort of ties into another question that came in, which was, does this provide a metric to the quality of the filter material? The answer is yes. And the same question was, are there instructions for constructing this? And they pasted in the link to the question on the Rapid Solver site, and the answer is yes. That's what we'll have up there by Wednesday. I did want to bring in Doug Stern, who was in the previous video with Bill Oley talking about ventilators, because Doug is a product designer and manufacturer in Providence who has done extensive work with compressed materials, such as taking. Well, you can talk about it, Doug. You've made, there it is. You're muted.
Mute. Hi, how are you?
Doug,
Hi.
meet Irene and Mandir.
Yeah, hi. So I have a business in Providence where for years I'm doing product development, but I'm also doing a lot of mold making and making of different things. So my shop consists of a lot of CNC equipment as well as hydraulic presses and RF welding. And part of what I've done over the years is a lot of non-woven products. So I've done a lot of molding of non-woven products. This is just a small example. I started playing around with hemp fiber and canaf and working with some other companies with binding agents and making non-wovens. So this is something that I am working on, the emergency ventilator with Bill Oley. But this is something that I was actually I had on the back burner, and I said to myself, I could be making a non-woven mask very easily, or not as easy. I mean, I know that it would take extensive testing. So I'd love to talk to you further on that and possibly work on that. But I do have a question though. I love your presentation. I love what you're doing. I almost bought a cotton candy machine myself, but I didn't. I had enough machines. So.
I have one. We can share it. We have already got one here.
So, but I did have a question. So from my research, the N95 masks, the reason they work is the electrostatic portion. It's a melt blown non-woven polypropylene, and it has an electrostatic charge to the inner layer, and that's the reason that they are supposedly so effective. So my question is, and I'm more of a natural materials sort of paper person. I really don't want to be getting into, although I'm very passionate about finding ways to use, recycled plastics. But so my question is, with the paper approach that you're taking, could we, or could you, in the past, I've done a lot of plating, and could we take some sort of medium material that is platable to be able to, or can hold an electrostatic charge to put some charge to the paper? Is that not feasible?
No, it's feasible. And I'm trying some other materials to impregnate the paper with these materials. So as far as the electrostatic charge is concerned, yes, N95s probably do that. They do that, not probably. I'm considering that as a black box for now.
Okay.
I'm just looking at the input side as being this incense, and the output side as being what comes through to the detection chamber. Now, on that basis, we are trying to get an equivalent performance. Now,
I guess that, yeah, that's great, because it's a lot more effort to make the electrostatic. Yep.
I think it is, and there are different materials that could be coated. But again, there's some material that was just some coating that was announced by the University of Pittsburgh. We're trying to get hands on it so we can coat some of these. I think if we can create materials that have, say, 20 puffs, 40 puffs, and are breathable, then any coating we put will make the breathability slightly less, but will increase the performance. So that becomes a secondary operation. After we finalize the material, we will look into it.
Okay. No, that's great. Anything I can do, I can.
Absolutely. Yeah, I'd love to talk to you.
Okay. Thank
Great.
you.
Thank you so much.
All right. Well, thank you. Thank you, everybody. We're about 4 minutes from needing to start our next presentation, which is the Community Feedback Loop panel. That was a pre-recorded panel, and the time's a little tight, so we won't have time after that for interactive Q&A, but I would ask any panelists who are here to participate in the chat if any questions come up, or Q&A as well. I think you can see Q&A, but if not, I'll let me know, and or if you can't answer, you can see Q&A, but if you can't answer it there, just let me know and you can answer it.
Q&A.
Oh, great. And are you able to answer as well?
Yes.
Oh, great. Perfect. See, I don't know anything about Zoom. Great. So we're going to start that in 3 minutes. That is a jumbo Brady Bunch style presentation on lessons learned. Well, Annette, Valerie, Dee, do you want to, we have 3 minutes. We could, if you want to introduce the panel. Thank you, Irene, Mandir, and Doug.
Okay, bye. Thank you.
And everybody's muted, so.
I will say that
all right.
all of this wonderful engineering work and the maker work that went on actually needs a place to go. So the next panel is going to be talking about how do we get it out into the world, and then actually get feedback from the people and send that back to the engineers in the 3D printer and the makers. That's what this is all about.
All right. Well, fantastic. All right. So I am going to get the screen share and all that
He's
fun
done.
stuff.
I'm going to kill her. Katie, this is like the 10th thing I've had to deal with today.
Oh, where we've
Thank
got a
you
hot
for being a
hot
voice
mic.
of reason.
We have a. There we go. Okay, I'm going to get that going, and we will see you after that. And then there's one more panel after, one more presentation after this.
Welcome, everyone. We are going to be talking today a little bit about the Rapid Solvers group in Rhode Island. And I'd like to start by having everyone on the panel tell us a little bit about yourself and how you first heard about the Rapid Solvers group.
I'm Annette Tonti. I'm the managing director of RIHub, which is Rhode Island's innovation hub. And our role here actually is as a connector. We spend a lot of time in the Rhode Island region helping with all things ideas to startups and startups to help basically create an ecosystem here. So we spend a lot of time in relationships with the entire ecosystem. And so when I first heard about Rapid Solvers, it seemed like, and it was at the moment that we all just sort of understood this was a pandemic and very serious. So it seemed to me like the thing to do was to bring to the table what we could do best, which is connecting.
My name is Ben. I'm an electrician and a father and just kind of like a regular guy. When this whole pandemic started, I kind of was looking for a way to help like many other people. So I decided to found the Rhode Island 3D Printers Alliance. And basically I had the same thoughts as everyone else here did, and that's to connect people with the same ideas to kind of create the PPE and help other people. So basically within the first couple of weeks, we just kind of found people throughout Facebook and online, and there was little, not printer farms, but individual people doing one printer here and two printers there. And so the grand idea was kind of same thing, bring everything together. About the same time, I found the Rapid Solvers on Facebook, and I sent an email to Kunal, and we connected that way, and he said, hey, listen, I got this Rapid Solvers going with URI, and I think you and your group would be a great fit. And here we are today.
Hi, my name is Erica Usman. I am the manager of Makerspace URI at the University of Rhode Island. I got involved with this because I got linked in on an email about starting to make PPE, and there already being a group on campus that was trying to get that together. So that's how I got started with it.
Hi, my name is Tanya, and previously I was the lab technician for the biomedical engineering lab at URI. I had left URI a few months before the pandemic started, but I had all the skill set and I knew URI had all the resources. And so I also had seen Kunal's, everything Kunal is doing. So I reached out to him, and they were gracious enough to let me back in and help me set some things up.
Hi, so I'm Dee Dee Chatham, and I work every day to launch innovators and entrepreneurs at Rhode Island's flagship university, the University of Rhode Island. And as part of that, I work with a lot of the faculty, and was also involved with the faculty in the College of Engineering, who had started this group to produce PPE and to just sort of see where it would go. So it was a natural fit that I joined in, and as with everybody else, sort of like, what can we do that can help and have some kind of an impact?
Thank you. I'm Seiji Abe, lead technologist for Fab Newport and PVD Young Makers, which Fab Newport is a nonprofit community makerspace, and PVD Young Makers is our initiative with the City of Providence to run makerspaces in the 10 public libraries. So we normally are running programs using 3D printers and a lot of the other laser cutters, a lot of the other technology that's being used to make this PPE. And as soon as school was canceled, we realized we weren't going to be able to do our normal programming and have the kids in, we wanted to find a way to put our equipment to use. And it was just really a natural fit very early on. We were already hearing that people were sharing open source designs and making PPE. So I looked into that. My boss, Steve, reached out to the community of makers Rhode Island, which is actually pretty small. And he connected with Rapid Solvers pretty quickly and had me take over with the project. So me and one of my other colleagues at Fab Newport have been producing face shields, and we've made over 4,000, made and donated over 4,000 now. And it's been great ever since working with you guys. I'm so glad we found this group.
Hello, everyone. My name is Dylan, and I'm currently an MBA student now at the University of Rhode Island. I'm also an community outreach coordinator with RI Hub, with the NET. I got involved with Rapid Solvers because my undergrad was in biomedical engineering, and I did research with Dr. Kunal. And but because of that, I heard about this group through RI Hub, and then reached out to Kunal again and asked if there's any ways I can get involved. And because of that, I was able to help build out the group's website as well as connect some people. So it's a fantastic opportunity, and I'm glad to be taking some of the skills I've learned and actually applying them.
So I'm Valerie Meyer-Spiritolozzi, and going to be moderating the panel. And I'm a faculty member in the Industrial and Systems Engineering program at University of Rhode Island. And you heard a couple of our panelists refer to Kunal. That is Dr. Kunal Mankodia, who is faculty in the Biomedical Engineering program at University of Rhode Island. And he kind of started pulling together the Rhode Island Rapid Solvers group by first emailing a group of faculty and then reaching out to the community pretty quickly in March when the virus began to spread in our state, and brought together people who were all interested in helping in whatever way we could, and identifying where the resources were at the university and around the university to bring those together. All right, so to follow up on that, let's talk a little bit about the 3D printing itself. And part of this has involved sharing and improving the .stl files between companies, universities around the country. And so I'll ask a couple of you to talk about your experience in finding those files, deciding which ones to use, and improving them, and what that involved.
I know for me, it's been a constant process of innovation and collaboration. From the beginning, we just pulled our first design off of one of the websites we found online. It was the Budman design, which at the time was one of the first ones that had been approved by the NIH. So we thought that was a good, safe bet to start producing. We made a couple hundred of those, and then Didi was nice enough to invite me to come to a meeting with one of the guys running the donation station for the Department of Health. And we were able to get feedback based from them on the Budman design, but also a newer one that we had just started printing, which is, you know, pretty much the basis for the design we're doing now. And he pretty quickly zeroed in on the newer design as being more efficient, easier to make, and probably easier to clean as well. So that was a big factor in informing us on which design to use, even though at the time that one hadn't been approved by the NIH. I believe it has been now. And even once that was approved, we, you know, working within the group, we all collaborated to improve the design and make multiple stacks so we could print them faster. So it's been...
Yeah, we were surprised that first day that that was the one that he liked. We didn't go in there thinking that, but he said, wow, this is going to be the easiest for people to use. So it was great to get that early feedback from someone out in the field.
You know, that's also one of the advantages of being in a group like this is the sharing of files. Coming in myself and my group as an outside kind of set of eyes, we were able to look at the designs you guys had kind of worked with and gotten feedback from and put it to our people too and get our own feedback and kind of work with those designs and, you know, come up with the same consistent things so that we are giving the same product that you guys are, all making kind of a uniform, in this case, face shield.
I think that that's making it easier as we go along too, because now we're starting to get groups who are asking for the next round. They've sort of gone through what we've given them. And so to give them the same thing, again, it's easier for them to have that same format.
Any thoughts on the improvement of the file itself or the printing logistics?
We personally faced a few challenges with printing designs other than the Prusa design in the makerspace, mostly because we're dealing with smaller printers. So the things that have the earpieces that come back instead of the straps tend to get a lot larger. They work better for the actual Prusa printers, oddly. So we've been mostly doing that style, and then we also started working with the Apple face shields, which are a laser cut design instead of the 3D printed. And those are very fast. Those are a couple of minutes each. And the only difference is the material gets a little bit more expensive.
That's actually a good point she just made about the smaller printers. My colleague has all of our printers that are big enough to print the shield piece in one section. The printers I have are Key X12s, and they're 140 squared millimeters. So we had to break down our design. This is the overall piece we're doing, and ours had to be broken down to 3 pieces. So we have 2 side pieces and then a center piece that fits together with that. So that's been one of the big things that we've had to do kind of independently. But I think the other biggest improvements that I saw coming out of our group collaboration was changing from the 6-pin to a 3-pin design to make sure that it was easier to produce the shield piece and punch the holes, and the stacks for printing faster as well.
Didn't we also get some feedback directly from the users about the comfort level of one versus the other? And so we could kind of iterate on, kind of getting it done, getting it out to the field, and then turning around and actually making changes based on the comfort level that the actual frontline users were experiencing every day, which was also a consideration, obviously.
Yeah, at least one of the users said, "Oh, those are so good. They don't give me headaches like the other one did by the headband being into their head too tightly."
That's important. Yeah.
Mm-hmm.
Yeah. So to summarize then, some of the improvements and iterations in the design process included incorporating that feedback from the users. I know we've had some users say that they're the best face shields that they've been able to get, even prior to the virus pandemic level. So that's been really great for us to hear. And also adjusting it for the type of machines that each person had, and improving the number of shields in a single print stack so that our time was more wisely spent. And then finally, adjusting it for the type of printers. The next topic or next question is going to talk a little bit about sourcing the raw materials and getting everything we needed in place to build these face shields and other components, because we have explored a few other types of components that would help the healthcare in the area. So how did that work for you, given that there were some shortages of certain materials and delays in transportation because of the virus?
I think that goes back a little bit to the last question. A lot of our designs were mostly based on the materials we had available to us individually. So our previous original design was the Prusa design, which was, I don't want to say over-engineered, but it wasn't a good balance in terms of time management. We could produce a good shield, but it took quite a lot of materials and it took quite a lot of time. And the big thing with that was we were considering doing the elastic, because most people were doing that. But of course, that was one of the materials that was the hardest to find. And so we came up with our own strap design that had laser cut holes in it. One of the big reasons we switched to the newer design is it was mostly a 3D printed part. So apart from the face shields, we didn't have to worry about anything else.
Yeah, the cloth mask makers snatched up a lot of the elastic all across the country really fast, I think. And suddenly there was no more sewing elastic to behold or to be found, or bias tape either. Seiji, the design, can you hold the design up again? I think some of what the healthcare workers like about this is that it fits, we did some anthropometric testing on it, and it should fit the majority of folks from small head circumference to larger head circumference. And if they need to hold it in place with an elastic or something in the back, then they can, and that's usually readily available to people.
I just wanted to say also that you know, at one point early on, there were up to like 80 people coming onto our like bi-weekly calls. And so this is like a nice group for a talk right now, but I mean, the larger group, and early on also when people were having trouble getting materials, there was some sharing going back and forth between community groups that didn't even know each other beforehand, just to keep everybody producing. So that was.
There was a great deal of discussion on, you know, where to buy the material. And then also, I know we're not talking about face masks at this moment, but there was an enormous amount of work on materials that could work at like an N95, you know, kind of capability to basically after you 3D printed the face mask that you could actually find material that would be able to keep the virus out. So just the materials piece, as Dee Dee said up front, we would have a ton of people on those calls, sort of all talking about various different types of materials they needed. So it's pretty.
I think we were like really kind of iterating on what's the most effective thing that we can be doing. And we, you know, so this group was very instrumental in going forward with the face shields, but there were other groups that part of Rapid Solvers that were working on other things, like you say, the masks and even ventilator projects and other things.
And I just want to add, in the very, very beginning, when we were all together trying to figure out what's the best, we didn't know. After a few weeks, we weren't exactly sure what was the best use of our time. We were looking at all the possibilities, and to the point where the team then kind of splintered off, rightly so, into separate groups, because we ended up being the face mask group. And I'll say I think Dee Dee knows the exact number, but over 7,000 of these have been delivered so far. We've actually put another 500 in today, at least I did. So this continues. It's the need for 3D printed face masks in our region. Definitely we're filling a real need here.
So that brings up another good point. How about forecasting the demand and the order tracking and fulfillment? And that's a lot of, I know Annette and Dee Dee have masterminded that.
That's really hard.
It is.
Well, having always been an entrepreneur, I'm very used to ambiguity and operating in uncharted waters. So, I mean, it's pretty much, it's been hard to know how much demand there was going to be and how long it was going to go on for. But we're still in the middle of it. Like as Annette said, we just got another request for 500 today. There's about 1,000 where we still have on our list that we will be delivering over this next week.
So what we're actually doing now is we understood what we could make. And now we decided a few weeks back that we could proactively call out to home health care, senior living. Those entities need them badly. They really weren't being given these. So that's actually where the demand is now. Early on, we were at police, firemen, policemen, those kinds of entities. Now we sort of switched to home health care and senior living. And I actually didn't know how many there were, but we've got somebody who really is just dedicated to do this. She's a volunteer, and she's contacting them daily, and hundreds at a time. The real need is there. So it's kind of interesting to watch this, because it's not like a real business, but we've now gotten to the point where we're kind of creating that demand. So
I could see this continuing for a while too, especially as things are starting to open up more and more in Rhode Island. People are going to want more protection and to feel comfortable to go out. So I guess we'll see what our next group is that's contacting us the most.
We just got a request from the Master Gardeners group who are out teaching courses, and they were told that they had to, in order to run their classes out in the field, they had to have face shields, not masks, but shields. So, yeah, I think
initially the first requests were from first responders who heard about this, fire and police and EMS crews who needed face shields on top of their N95 type masks to prolong the usage. And it has definitely grown and shifted more towards home health care. And now it'll be going more towards community groups, I think, and stores or retailers or places like that who want their staff protected.
We actually just got a 250 requests from Metcalf schools. So I think a lot of the schools, like elementary schools, because they're going to have to be probably temperature testing children, they're going to want face shields. So that's kind of, we're thinking that's another group that's going to need them soon.
And I think that the initially twice a week or weekly phone calls with the larger Rapid Solvers group did help to identify who had certain resources at different times, or where the demand was, starting to fall off or picking back up again. And in particular, when we had larger orders, it was like, oh, well, we can't meet that from this particular one location, but this other location already has 50 or 100 ready to go. So coordinating that really has been great. And again, these are groups that previously didn't even really know each other existed necessarily.
And what was really fascinating to me in the early day was we'd have a Friday afternoon meeting and a Monday meeting. And on Friday afternoon, all the discussions happened and sort of engineering in real time. And 3D printer folks would go off, do the 3D printing, test them over the weekend, come back and give us the results on Monday. I've never seen anything like that. And it took really the 3D printing expertise and engineering and sharing of files to make that happen. But it was innovation happening in real time. It's really great.
It was also a little bit of, running small pop-up production facilities, but really, and at times running them 24/7. So would anyone like to speak a little bit about setting those up?
I know as far as with Fab Newport, we just kind of found wherever we had space. So the place I'm printing, Providence Community Library, was nice enough to let us use their basement. All their branches are closed right now, but we're able to use the basement at Rochambeau. So we collected all the 10 different printers that we have, one at each of the 10 libraries in Providence, and brought them there. And then my colleague had a couple printers at his house already, and we purchased a couple more. And he's just been printing out of his basement at his house. So wherever we can do it, but it's been, it was kind of a scramble at first to get it set up, but I'm really impressed by how all of us are constantly improving. And like you mentioned a second ago, at the beginning, we were kind of running them 24 hours a day, but I feel like now we've kind of streamlined the process and gotten to a point where when demand is down, we can kind of take a breather. And then as soon as the demand comes back, we just spool right back up, and we're able to run much more efficiently and quickly to do those kind of big orders and get them done. So it's pretty impressive how we've gotten to that point.
Mm-hmm.
And I mean, it's been amazing, just sort of the whole civic involvement part of this project, really, because I mean, you think about it, there are students or faculty, they're community members. We have a retired nurse working for us, helping to find demand, high school teachers, just entrepreneurs, industry. There are some companies that are working with us. There's Fab Newport. And in terms of, everybody was sort of pitching in too to kind of help distribute these, because some people couldn't come to pick them up. And so then we had, I have a grant writer from the URI Foundation who said, I'll go drive around for you and distribute, and deliver these. And I know everybody's been doing a little bit of delivery and a little bit of, so it's worked out really well to have something where, a student could walk in who hadn't done anything before, really, and play a part and feel good about their impact.
Like Dylan, who was here very specifically to help us with the website. Thank goodness. Seriously, it was a big deal just to get a website built. And Dylan stepped up and got it done. So that was great.
And that was the beautiful part about this experience, was that everybody could have a role to play, throughout, and just the level of collaboration. And then like you said, it's also empowering when you're able to step into these roles and say, hey, I made this impact and contributed to this thing. Yeah. Whereas, maybe someone could say, oh, we have this super important project, but we don't want students because they're not ready or something. When it comes to this real world need and this need for rapid solutions, everybody has a role to play, and it's not, so there's no type of qualification or not. It's just everybody coming together.
I will definitely agree with that. I will say the thing that has impressed me the most is, like everyone said, is the amount of people that are just willing to come together and try to figure out and make this work. When I first had the idea to just, have a little 3D printing group, I figured it'd be me, maybe a couple of my friends, but as soon as the call went out there to help, people jumped right on. And as you can see, it's not just the university, it's not just faculty, it's not just individuals, it's everybody in the community coming together and trying to play a part and help. And most of the time, it's from the goodness of their heart. Like, nobody's coming out and saying and looking for anything. They're looking to just help.
Yeah, it has actually really given a lot of people different ways to contribute and just feel great about being able to do something. We might be stuck in our individual houses here, but we're each able to contribute something. I know that I coordinated and communicated with a lot of people who had old transparencies in their offices around campus, and we had the police department who initially contacted us, the campus police contacted us to donate some of their transparencies from their supply closet. And then suddenly it became apparent that they could actually help us go collect those from buildings that were locked all around campus. And so anyone who wanted to donate some of their transparencies for the clear face shields could just leave them in the lobby area or outside the office door, and the campus police would go around and get them for us. And so it made a lot of people happy to be contributing. Undergraduate students, graduate students, faculty, staff, administrators, everyone really on campus, I know, has come together. And we've had retirees contact us, just like the retired nurse you mentioned. We've had some retired faculty and other employees still on listservs who said, hey, are you collecting transparencies? We can donate those too. So that's been great.
And I think that's beyond just the impact we're able to make right now, like making face shields and distributing them and these types of things. I think one of the biggest impacts of this group has been the networks that we've created with it, and just the like strengthening the Rhode Island community in general. And that's part of like RI Hub's work, is to try and defragment this ecosystem of just people, like, you know, Ben said, people are just doing their little thing over here and over here, but it's like when we come together, we can make a lot more happen. And now we have the actual infrastructure to do that.
Yeah, and I think like Erica said, I mean, with Rhode Island, I mean, Rhode Island's on the verge of, you know, we're just starting to open up businesses and schools, daycares, and summer camps. So it's nice to have this group in place to see if we can continue to be helpful.
For Fab Newport and my organization as well too. We talked about this a little bit in our group, but we've been trying to start a social enterprise that would involve students and makers and experts from the community all working together to make products that have value or be a rapid response team like we have here. So the next question for us is, how do we make this sustainable after COVID, even if we're not making PPE anymore? How can we get the community together to still be making products that are needed and involve students and get some education going?
For each of you on the panel, just what was your biggest, I think, lesson learned from being involved in Rapid Solvers and in this collaborative effort?
Well, for me, I've never seen anything like it in terms of the types of people from all different areas, including we had emergency physicians, we had physicians that had inventions on there, as well as our 3D printers, et cetera, faculty, students. And I think the amazement to me is how well a fairly large team gelled really quickly. And I remember feeling in the first couple of weeks like, do we know what we're doing or where we're going? But it needed to feel that way for a little bit until we kind of got it together to say, there's 3 groups, you know, face shields, face masks, and actually there was a group that I think they're still working on it, 3D printing those kind of adapters for CPAP machines to make them into, respirators and such. So we suddenly had to split, but it happened so quickly. And I think it's that from all of that discussion, actually out of that came some clarity, and engineering enabled that very quickly. The 3D printing enabled it like I've never seen before. You couldn't do it without the 3D printing piece.
Yeah, I mean, I agree. It was like really, I loved the whole, like the iteration and action, but also the whole early like customer development, like having people involved in healthcare and in hospitals commenting on what we were going to be producing, and then, going to the Department of Health and showing them and getting their feedback. And, that's just how you're supposed to be doing product development. It's right there, it's like early customer development on that. And we were able to do that faster than I've ever seen too.
There's a lot of creative problem solving that happened within this group. And I think for students or staff or really anyone who's been involved with it, that's like a big takeaway to be able to say that you can do that and to just get an idea going and sort of go for it and be willing to change it if it's not working.
And I think a big thing too is that it really is a true collaboration. Everyone's throwing their own ideas in, everyone's got their own feedback, their own input, and everyone's taking those ideas and they're applying them in their own ways. For instance, my group came in from the outside and my ideas are just used just as much as yours, and we're all working together, and that's the biggest thing. It's the collaborating effort, everyone's minds, everyone's groups.
Yeah, that speaks to the biggest takeaway for me too, is just how amazingly efficient and strong a group of people that are very passionate and share the same kind of goals can be, when they put their mind to it. It's just really amazing how a group as big as 80 people at some point was able to self-organize. Everyone kind of, naturally gravitated toward their areas of strength, and we really needed all that. There's the people who are actually making the masks, who are doing the production. There's the people like Dee Dee, who are like, she's the glue holding us together with the communication and everything, making sure the mask gets everywhere we need it. Other people just supporting us with recommendations, advice, supplies. And there are organizations and businesses that have whole business plans that don't operate as smoothly as this has gone, I feel like. So it's just amazing when you have passionate people, what can get done.
Right.
To echo that, I think the biggest takeaway for me or lesson to learn is that this is all possible in the first place. And it came at a unique time where I went from like being an undergrad to graduating, and it went same thing here with like all this theory about, studying, we can eventually help people, to like, now we're actively participating in this group that, this is how many face shields we've made and how many lives we've changed because of that. And, it's just very empowering for myself, and I think everybody else has been involved to recognize that, hey, we can do these things. And it just takes a matter of that time and energy and that spark of inspiration. And then it's met and it comes together and it just explodes into this beautiful thing, to where we're on this Zoom call now on a panel about the things we've done, and we're going to, broadcast this to the world. That's incredible.
I think I'll just add that it's a learning experience for all of us. It doesn't matter like how qualified you think you are. We're all still learning. And I would say that even like one of my best volunteers has never 3D printed in his life before this. And he's turned into like a crucial part of at least my operation.
And I think I'll just add or summarize too that we've done all of this with, trying to maintain safety and social distancing. So I think probably of all the people on this room, only maybe one or two of us have ever met in real life or been in the same room together ever. I'm guessing here.
Well, I got to meet Seiji in the most torrential downpour in a big parking lot where the Department of Health was collecting equipment.
I think, I know I've personally, I think only been with Tanya ever, no one else on the call perhaps. And so, we thought very carefully too about, how many people would be in different places, trying to make sure that there was some level of bringing 3D printers together to make it easier to monitor them and set them up. But also we consciously thought about having multiple locations in case any one of them got compromised if one of our own group got sick. And so making those thoughtful decisions as a group and taking input from folks who thought of these what if scenarios, or how can we best meet the needs of the community and use our resources together. So that was some of the major takeaways and things that we've been able to accomplish as a Rapid Solvers group here in Rhode Island. So I want to thank all of you for being on the panel and providing your input, and also for your contributions to a great need here in our state. So thank you all.
Thank you. And we all want to go to Ben's backyard. It looks pretty nice over there.
Barbecue.
Yeah.
Let's go. After COVID.
In 2021, right? As soon as the governor says it's okay here later.
Maybe Christmas.
We'll all have enough face shields.
That's true.
All right. Well, this takes us to our last session, and I'd like to introduce Alex Hornstein with the Ventilator Project. Alex, are you ready? This is, I should say, this is the last presentation for this session. There's much more, virtually Maker Faire, many more hours of that. So don't leave them, just leave me. Don't leave Alex now. I think he's ready.
I'm here. Can y'all hear me okay?
I can hear you great.
That's great. Is that thing forwards or backwards behind me? It's one of the
It is forwards. It always looks backwards.
Oh, good. Okay, I'm going to share my screen.
All right.
Okay. Sorry. Beginning to. Oh, there we go. It's hiding behind Zoom. All right. Can y'all see everything here? I'm like a big walker around as we go. Okay. Here we go. Okay. So my name is Alex Hornstein, and I wanted to give a little bit of a rundown of some work that we've been doing here, based in Rhode Island, but now working across 10 different countries with an organization I started called Ventilator Project back in early March. So, oh, and just a little bit, this is me. We don't have to talk about me that much, but I don't do anything in healthcare. This is very, very new and different for me. In normal times, I am CTO at a holographic display company called Looking Glass, and I do a lot of work in product development. And I've also spent about a decade working in rural infrastructure development, where there is no doing, not healthcare, but doing electrical infrastructure in the middle of nowhere, where there is no electrical grid. And thinking, and was very kind of familiar with this idea that infrastructure is not there for a critical need, and how do you put it in quickly and effectively. With me, but he's tied up on a call right now with Nigeria, is Dr. Fenton. So Dr. Fenton's been one of 75 volunteers who have helped, but Andre's been a huge help from the beginning, connecting and giving feedback and helping us as we start working out how you can quickly get something that is not entirely a ventilator, but something that can be used by doctors in hospitals and get them into hospitals. So Andre is, like many folks in this group, I had not met in person or had a chance to work with before starting this. So as I think folks are mentioning, this is actually very extraordinary of having a lot of folks who are very willing to help and who can really jump in, and Andre is exemplary of that. So I want to wind up a little bit back to the beginning of March, where we start seeing news stories saying that we need 600,000 ventilators in the country in 2 to 3 months to get through the surge. And I think the wake-up call for me was seeing Governor Cuomo go on TV and say that we need a bunch of healthy volunteers to wear PPE and squeeze an ambu bag forever for patients who need ventilatory support. And myself and my partner in Looking Glass, both of us have a background in respiratory, or not in respiratory care, in developing world technology. And we're like, this feels like there is a very strong shortage of devices. Like, this is a big wake-up call for us. And so we started to think about how to quickly work with it. I started to understand, like, as we're seeing these stories come out, all the stories say, we need all these, the companies that make ventilators aren't going to make them in time. How do we get them here? And it wasn't clear that anybody had a fix for what you do if you are at a surge of ventilatory patients or patients that need vents in hospitals, and what the plan was if the high-end hospital vents didn't show up. States will put together groups of everybody in their state who knows anything about ventilators. These are doctors, respiratory therapists, state board of health, folks in the industry who know how to source and where the stuff is made, and often folks in Rhode Island, it's Rhode Island Commerce Corporation, who are in charge of using state funds to procure vents. It's not super clear what the federal government's response was in this, and I'll kind of get more into this as we go. Early on, I saw this very interesting write-up. I'll share these slides later for anyone who wants to go through this, by a hacker, a maker, Johnny Lee, who's now at Google, who took a CPAP. He happened to be on a CPAP, and he took it apart and he looked at the motor and he said, I'm going to drive the motor and I'm going to measure what the motor can do. And it turns out it's actually the motor at the core of these CPAPs is very capable or very similar to the motor at the core of a ventilator. And I guess before getting into jargon, what is a CPAP? So there are these home use machines called CPAPs, as well as slightly fancier machines called BiPAPs that are used to treat sleep apnea. CPAP stands for continuous positive airway pressure, a BiPAP, bilevel positive airway pressure. And there's a lot of them. So spread across the states, there's about 8.5 million of these machines. And they're not ventilators, but they do a lot of the things that ventilators can do. And that idea that there's a shortage, we can't produce ventilators in time, but maybe we actually have sufficient machines that are in the states and also in the world to meet this very pressing need. That hit me very early on after reading this early Johnny Lee write-up. And that write-up was written for, it's like a GitHub page. It's written for makers. It's not written for doctors. Doctors look at this like it's a pile of wires and hot glue. It doesn't look like a thing. Like he's using a manometer that uses Diet Coke as the water in the water manometer to show the pressure that this is able to put out, which I love. No, it wasn't Diet Coke, it was Diet Dr. Pepper. But like it doesn't present well to a hospital, but it is a very good proof of concept for an engineer or a maker. So the kind of interesting bit as we started diving in, my first takeaway was I just need to talk to every pulmonologist and respiratory therapist, every single person I can talk to. And not knowing any of them, I don't work in healthcare. I reached out to my social network and I said, to any friend I had who was connected in healthcare, I was like, let me talk to a pulmonologist. And this led to basically 2 straight weeks of nonstop talks with pulmonologists, trying to understand how do you actually use a ventilator in a hospital? What are the ins and outs of this? And the vent, of course, is kind of the blower side of it. There's also all these things that connect to a patient called the patient circuit, which is like the tubing in between that, and the interface that actually goes into like a mask that goes over a patient or an endotracheal tube that goes down into the patient's lungs. And ventilators can do all different sorts of things. And this being a new disease, nobody really knows which of those things in the spectrum makes sense. So starting to look at papers coming out of ICUs, these are this whole spectrum of treatment, starting with a low flow nasal cannula. This is a very simple, put a cannula into your nose, connect it to an oxygen tank or a wall oxygen fitting, flow a small amount of oxygen in. And what they would do in hospitals is they move through this treatment. Every doctor goes through this and knows to kind of, you want to use the least invasive treatment possible. Now in Wuhan, that's exactly what they did, because this concern over how infectious COVID can be was not super clear in Wuhan. And shortly after Wuhan, the heads of the WHO and the CDC put out this notice that says, if you look at everything here in red, they said, we are concerned that this could aerosolize the virus. So if you put a lot of air into the lungs and the lungs are full of virus, we are concerned that that could come back out into the air and expose the healthcare workers. They said, don't use it, basically, or that was the takeaway. So every hospital jumped from this relatively low capability treatment, which is a low flow nasal cannula, and really quickly moved into a very, very invasive treatment, which is full intubation. Even in the US, we talked about an early intubation policy, which basically meant if the low flow nasal cannula doesn't work, intubate. What was interesting here is, like everything, this is a very nuanced story. And so these ideas here are interesting. These do not have this risk of aerosolizing a virus. A non-vented mask lets you put a viral filter on the mask that can keep the exhaled air, that can filter out virus and bacteria particles from the exhaled air. And an oxygen helmet is, you can think of it like a 5-gallon bucket you wear on your head, but these were used extensively and reported extensively in Italy. There's large-scale clinical trials going on right now in the US, led by the University of Chicago, and they make an airtight seal with kind of like a dry suit seal or a latex seal around the neck, and they have an in tube and an out tube, and you put a filter over the out tube. So both those can mitigate the risk of your healthcare workers being exposed to virus, and that's critically important. Okay, so, and then each of these outcomes, this is from a paper that came out of the Wuhan ICU, and there's many that came out of Italy, there's many that came out of New York that have very similar numbers. And it talks about, as you move through these treatments, what's the prognosis for a patient? And these are super complex numbers to think about, even for doctors, because it has this dependency that says, if the patient can get better on this, this is their odds of survival. And that is a complex idea to grasp, because it doesn't mean that one mode is better than another. The thing that the variance is how sick the patient is going in. And a doctor will always do whatever they can do. But some of these, if the patient is so sick that ECMO, the extracorporeal membrane oxygenation, that says your lungs are so non-functional, we have to take the blood out of your body, put oxygen directly into the blood, and put it back in, put the blood back into your body. That is a very, very invasive and a last-ditch effort, and it has poor odds of success, especially with COVID. A lot of invasive treatments with COVID have very poor odds of success. I looked at this, and I think a lot of different folks looked at the ventilator shortage and had different approaches. Mine centered around, don't make a new ventilator. There's actually like a lot of large companies that have invented ventilators, and they are working very hard to produce them. And they have this problem of centralized production is a bottleneck right now. And if it's a bottleneck for these companies that have been doing this forever and have been around and have all the experts in the world working on it, why would it be better for a brand new company? Apart from optimism, or apart from being able to move quickly, which is a huge thing that smaller companies can do that large established healthcare companies struggle with, this is a problem. But I looked at this and I thought, this is not an invention problem. There are ventilators that exist. This needs to move the things that exist into hospitals and communicate how to use them effectively, and also learn about how to use them effectively. Anything that leads towards centralized production is going to get stuck the same way that we're seeing ventilator production get stuck. Let's use what's out there. Now, I'm not the only one thinking about this. So in New York, as they're starting to go into their surge towards the end of March, some doctors in New York got together. They said, I think we're going to be out of ventilators on Monday. And they got together on Thursday, the week before, and they said, we have to figure out something. And they wrote a protocol for using these guys, home use BiPAP ST machines. ST stands for spontaneous timing. It's a machine that can breathe with you and detect when you try to breathe. And if you forget to breathe, it'll push a breath. That is very, very functionally similar to what a ventilator does. And they wrote a protocol for how you can hook that up to this exact same tubing that they use to drive a patient. It turns out, like, the patron saint of ventilators says all the tubing that runs into home use CPAPs exactly the same as the tubing they use with ventilators in hospitals. So these doctors wrote a protocol, and all of a sudden there's a bunch of doctors who signed up on it. So every one of the 12 public hospitals in New York circulated this, contributed to it, and it went through many, many rounds of very rapid iteration as the doctors and respiratory therapists started thinking about how to quickly put that into action. So where do you get these machines? They're cheaper, they're simpler than vents, they're commonly available. You can buy some new ones. So there are about 50,000 BiPAP ST machines, maybe, new in boxes around the States, somewhere in a warehouse, or you can get used ones. And there's probably another 50,000 high-end used ones in people's homes. And obviously you don't want to go take a machine someone is using. And I'll get into that. So where are these? I'm saying they're spread around. Where do you actually get them? So there's about 8 million CPAPs, 500,000 BiPAPs around the States. I learned this talking to basically every major distributor of CPAPs and BiPAPs in, well, everywhere I could possibly get in touch with, but including all around the States. And a fascinating thing you learn is that people don't love their CPAPs. There's some people who really love them and swear by them. And a lot of folks will try it and say, this isn't for me. I'm one of those people. I tried it and I thought, oh my God, this is like being waterboarded by a doctor. This is no bueno. And so about 35% of these machines are on shelves. They're prescribed by sleep medicine doctors and they're used for sleep apnea and COPD. And that's interesting because those doctors have a relationship with their patients. And if you wanted to collect these and use them, if you wanted to get donated machines and bring them to hospitals, you have to refurbish them. You have to clean them. You have to test them. You have to document them because hospital workers have never seen home use machines in many cases. And so you have to work this out. And then another big idea here is that there's not enough BiPAPs in America. Even if you took every single BiPAP, at the numbers we were looking at in early March, even going into early April, the models say you actually need a lot of machines. And so we started looking at these more plentiful machines, 8 million CPAPs versus 500,000 BiPAPs, and saying, could these be used? Now, the interesting thing, so the thing on the left is the most common CPAP model in the world. That's an AirSense. And they wholesale for $200 to $300. They retail for $600 or so. The model on the right is an Air Curve. That's the type that was used by doctors in New York. Those retail for $2,000 to $3,000. They look the same, right? The one on the left is the AirSense for her. You can tell because it has ivy and the mask is pink. But the machines look the same. And so we started looking at what the difference is between a CPAP and a BiPAP. And it turns out that they are the same. It turns out that they are identical hardware, and working with some extremely talented firmware reverse engineers, we got a lot of these models into their hands, and we had them look around. What they found was there was a hidden high-end BiPAP menu that was on all of the low-end machines. And the only firmware difference, if you dump the firmware between the cheapest, like $250 Air Start, the lowest end model, in the new the S10 line from ResMed, most common CPAPs in the world, and the highest end, like $3,500 Air Curve ST, the only difference was one word: sense versus curve. AirSense versus Air Curve. Every other binary file in there was the same. So that's something. And that kind of has a promising idea that if you needed these in a pinch, they'd already put that firmware. It's not even our firmware. Oh my, okay. They'd already put our firmware in, or they'd already put that firmware through FDA, and there was a possible way to get that through. So I'm gonna kind of skip a little bit ahead and just run through, if you have these machines, how do you actually get it into a patient? So with the BiPAPs, you use an endotracheal tube. With CPAPs, it turns out there was something you could do without even having to modify them that emerged, which is similar to what they did in Italy and Chicago, which is you drive these bubble helmets, these oxygen helmets that are non-invasive ventilation. And that's a very promising idea if you can make it work, because you don't have to put a patient in a medical coma like you do when you intubate them. They're awake, they have COVID, they're not happy, but they're awake, they're conscious, they're breathing on their own, and you apply a little bit of pressure and a lot of oxygen. And this felt like a very good fit. It's also, that's what most patients who need respiratory support look like. The ones that get worse and worse and worse are a smaller percentage, but the more extreme ones. The last question is, what does the hospital machines have? So there's hospital CPAPs and there's home CPAPs. What do the hospital ones have that the home use ones don't? Because we want these to be used in hospitals. And the big thing they have is they're being used as life support devices. And they have this alarm that tells you if something is going wrong. If the hose gets pulled out by mistake, or if the power loses, or what have you. Hey, okay, so I'm getting a wrap up. So are we done by 1, or should we get out right now?
We've got just about 1 more minute.
Oh, well, let's run through this. Oh, we just got to the fun part. Okay, we went and turned every fire station in the state into a CPAP BiPAP collection station. University of Rhode Island gave us a gigantic ballroom to receive and refurbish machines. We refurbished a whole bunch of machines. About 850 came through. Had about 100 student volunteers from URI, which was fantastic. Bundled them up into these evaluation circuits. Talked to doctors in now 9 different countries. Sent each one of those evaluation circuits. Had doctors put together a collaborative protocol for their use. Actually are at the point now where we have doctors receiving them in Haiti, Philippines, Nigeria. I was just off the phone with Nigeria. Working on getting pallets out to those doctors. And moving on to how you unlock larger aid organization to getting more of these out.
Okay. I gotta get Adafruit on.
All right.
So anyway, I know you gotta go. Thanks for your time.
All right.
What time?
Thank you.
No, that was John Parks. Just,
All right.
Sienna dropped the ball.
Okay, I'm gonna mute that hot mic there. All righty. Well, I think we're done. Thank you very much. Thanks, Make, for hosting us. And I think Alex just answered the one question that came up. All right.
Well, I was just gonna say I'll post in the chat here. Can I post that out?
Yeah, I think so.
All right, give me 1 second. I'll send them out.
All right. Take it away, Make community. Let's see what we got here. So this is